Welcome back to Integral Calculus. In this video, I want to go through the calculus of hyperbolic functions. Previously, we established the 6 hyperbolic functions, sinh and cosh given by these exponential definitions, and then the other 4 functions tanh, coth, sech, and cosh, which are all based on the ratio and reciprocal identities borrowed directly from the trigonometric function. I'll stick with just sinh and cosh here. Now that we have these functions, this being a calculus class, it only makes sense that we'll spend some time thinking about the derivatives and integrals involving these 2 functions. So let me get my head out of the way and we will dive right in. If I want to take the derivative of sinh, well, by definition, that is the derivative of the exponential mess. And using nice properties of linearity, yes, this is a rational, but it's just a number on the bottom. There's no variables there, so the denominator is a constant. We can factor that out. We can think about just the derivative of the numerator. We have some subtraction going on, so we can think about the derivative term by term. The derivative of e to the x is e to the x. The derivative of e to the minus x is minus e to the minus x. That minus and the subtraction that's already given will turn that into plus e to the minus x, and then the constant 1/2 will remain. And the important thing here is to recognize that this is just the expression for cosh. And then, if we look at the derivative of cosh, we will again start with the definition. This is the derivative of e to the x plus e to the minus x all over 2. We still have that 1/2 that's a constant that's just going to remain. E to the x, the derivative is still e to the x. E to the minus x, the derivative is still minus e to the minus x. We have addition currently, so that will turn into subtraction in this case. And yes, that is exactly the expression for sinh. Right? Very similar to the usual trigonometric functions. Derivative of sine turns to cosines, derivative of cosines turns to sines. But we don't have the positive and negative mess that is the hard part to remember for the traditional trigonometric functions. Derivative of sinh is cosh. Derivative of cosh is sinh. Period. End of story. No negatives, nothing else going on. And now that we have that, we can say, just by direct integration, right, if the derivative of cosh is sinh, then integrating both sides of this equation, we get that cosh of x plus some constant of integration that might show up when we integrate has to be the integral of sinh of x dx. And likewise, if we integrate that the derivative of sinh is cosh, then we get that sinh plus some constant of integration has to be equal to the integral of cosh of x. So very straightforward. We're familiar with how this works in the normal trigonometric functions. The hyperbolic trigonometric functions are going to be much the same. I guess the things that can get a little bit interesting are when we have expressions going on inside. So for example, if I want to take the derivative of x plus 2 cosh of 3x over 5, same rules of derivatives that we are accustomed to. This shouldn't be too difficult. Derivative of x is 1. Then we have a 2. Derivative of cosh is sinh. Same argument, but then multiply by the derivative of the argument. The derivative of 3x over 5 is 3/5. I would probably from here clean up a little bit and call this 6/5 sinh of 3x over 5 plus 1, but technically speaking, either version, either of these is the derivative, and it's a matter of preference and what's going to be useful in the future from there. Likewise, if we want to perform an integration, say the integral of x times sinh of 5x squared dx. Well, for this one, we might want to try something like a u substitution. In which case, du would be 10x dx. We've already got the dx and the x. It would be really nice if we also had a 10. So multiply by 10 and by 1/10 so that everything works out. And we have 1/10 integral sinh of u du. Integral of sinh is cosh, so we have 1/10 cosh of u plus our constant of integration, and then substitute back in, u is 5x squared, so all told 1/10 cosh of 5x squared plus our constant of integration. I know I'm going through these relatively quickly, but the process of derivatives and integrals should be old hat for you. This shouldn't be a challenge, except this next one will be. What if I want to take the integral of 7 times sinh of 7x times cosh of 7x dx? This is a mess. This is a product of two hyperbolic functions. There are two ways of going about it, both of which are fairly straightforward. I'm not going to say that one is better than the other. But I think that the easier of the two is to let u equal sinh of 7x. And as soon as we do that, then du would be 7 times cosh of 7x times dx. And yes, this is literally just integral u du, so we're going to get 1/2 u squared plus c. That's 1/2 sinh squared of 7x plus c. Now the reason I wanted to go through this problem is there is a completely other way of going about it. That other way is to remember that the sinh of 2u is 2 times sinh of u times cosh of u. So in this case, sinh of 14x is 2 times sinh of 7x times cosh. I ran out of space to write in the argument. 2 times sinh of 7x times cosh of 7x. We currently have 7 times sinh of 7x times cosh of 7x. But if we just multiply by 2 and divide by 2, we can bring the 7 halves out front, leaving behind 2 times sinh of 7x times cosh of 7x times dx, and rewrite that as 7/2 times the integral of sinh of 14x dx. We could go through a u substitution here, but the important thing is that we need an extra factor of 14. All right, so our 7/2 stays out front, and then we're going to have a 1/14 times cosh of 14x plus c. You can double check by taking the derivative that that actually does work out. You can simplify a little bit and write this as 1/4 cosh of 14x plus c. And I think at this point you see why I wanted to go through this one. We took two approaches to evaluate this integral. Both approaches are completely and totally valid, but they gave us very different looking results. But that's actually not a problem, because if we think about the double angle formula for cosine, we know that that will get us from the 14 back to the 7. Right, so this second one, 1/4 cosh of 14x plus c is 1/4. Double angle formula for cosh is cosh squared. In this case, it'll be 7x plus sinh squared of 7x. It would be really nice if we had just sinh. So from here, I will use the kind of Pythagorean looking identity. Remember, cosh squared minus sinh squared is equal to 1. So cosh squared itself is 1 plus sinh squared of 7x. And then we have the other sinh squared of 7x. That's 2 times sinh squared of 7x. So let's clean this up and write it as 2 times sinh squared of 7x plus 1 plus c. Distribute the 1/4. We have 1/2 sinh squared of 7x plus 1/4 plus c. That's really close to what we ended up with before. The first time we went through this, we had 1/2 sinh squared of 7x plus c. The only difference is this extra 1/4 term. But that's easy enough to account for, because we're going to add 1/4 and then we're going to immediately add an arbitrary constant. All that's really telling us is that the arbitrary constant in this expression is different from the arbitrary constant in that expression. If we just take the arbitrary constant in the yellow expression and subtract 1/4 from it, then we get the arbitrary constant in the other expression, because we have the extra 1/4 here. But we can merge all of that stuff together and we can call this 1/2 times sinh squared of 7x plus c. That is a long way to go for what really amounts to nothing. The real story here, the real takeaway from this, is that when you are performing integration or even differentiation involving hyperbolic functions, much like with trigonometric functions, there are several different ways that you might express your overall result that don't look like they agree with each other. But if you remember that you have trigonometric identities or hyperbolic identities, you can go through and you can rearrange to get from one to another. As you're working on practice problems, if you're checking answers in the back of a book, or if you're comparing answers with a friend and they don't seem to agree with each other, look for these sorts of things. Look for a place where you can use the Pythagorean looking identity or the double angle looking identity. See if you can get from one to the other. Sometimes it works, sometimes it doesn't. If it works, that means that you're on the same track. If it doesn't, another thing that I always recommend, going back to basic trigonometry, graph both of the expressions. Use something like Desmos to just generate the graph. If the graphs overlap, or there's just a vertical shift between them, it is the same integrand, or it's the same result of the integral. If they don't look like they overlap, or they aren't just a vertical shift apart, that tells you that there's something else going on. All right, with all that in mind, let's wrap up with one for you to take a look at, which will be the relatively easy option because it's a derivative. It is less likely to have multiple different approaches. But let's take a derivative of sinh times cosh. Right, just playing around with the rules of differentiation, some of the rules of hyperbolic functions. Take a few minutes, play around with that, and see where you end up with. And I'll see you in the next video.